Ah, okay. So let me tell you what we are ultimately focusing on. So I described a little bit of the symbolism of a black box. Yeah. So a black box would be represented so a black box would be represented by something like this. This would represent that something incredibly important happens inside, where this kind of things outside would be representing some trivial parts of the stuff. Inside, for example, nodes would be removed and so on, and this would sort of represent restrictions to simple things. Now, the main purpose of all this is, of course, that you ultimately can plug black boxes together. So you need some infrastructure to do this, and part of the infrastructure was that you could talk about, in this particular example, about the subannuli and so on. So a black box, if we look at one of those, the question is how much infrastructure do we actually need here? So if I have two black boxes which both have a blue line, so it means if they both have a blue line, it means we can talk about the restriction to the same set. Yeah? So this would be representing A. I have a restriction to A, I have a restriction to A. Then I could build the fibered product of objects here. And I want to put a smooth structure on the fibered product. The fibered product lies, if this thing here is represented by E, and this by E prime, then the fibered product, namely E cross, so the restriction would be phi. Here is a phi prime restriction. E prime lies in E cross E prime. These are all objects in here which restricted to the blue line are, so pairs of objects here and here, so that the restriction to the blue line is the same thing. So that's a subset of this. And I want that this inherits an M-polyfold structure. Then this thing would be hooked together, then I have still a few free ends. So this new object would be represented by something like this, where I contract this so the black box looks different, and I would have three things coming out of this. And it should be a new black box. And then if I have something like this and another black box, I can put them together, I can build a new fiber product, another black box. Right? So you want to be ultimately, whenever something comes out here, which is a common with this one, you could build some new black boxes, which represent some problem. Yeah, that's ultimately what you want to do. So the question is now, how can I guarantee that this fiber product is actually a sub-M polyfold of that thing here? In general, there's no reason why, because I didn't say too much about this map, that the fiber product has this property. So, of course, I could say, well, you can only compose two black boxes provided this fiber product is an M polyfold. But then you have to maybe go through the whole machinery and check this, that we don't want to have. We just want to have, if they geometrically fit together, they're fine. So what kind of infrastructure do I need? And the infrastructure which I need is actually one which you can describe for each black box separately and is not dependent on other black boxes. So the first thing, so we want to describe want to show that, so we have two black boxes, so we have this A, F, B, so we have these Cartesian diagrams, and we have another one, E prime, but it goes onto the same A, I require it goes onto the same B, here's an F prime, at least I have this. So part of the geometry that I can even plug them together is that this data here should be the same than this data.
is always the subannulus that's closer to the open
Yes.
vein. So the B's
Yes.
are different ones.
Yes, so yes, you're right. B0. Yes, it's different. So let me call this B prime. Yes, right. Good, good. Very good. Thank you, Katrin. No. Actually, I called that B0 above. Yeah, okay. So let's call this B prime for the moment. But you see, for the fiber okay, so for the fiber.
It's just to make sure everyone's on the same page. Label B prime on the orange lines where your diagrams of E, A,
Oh.
E, F.
Yeah.
Label B prime.
Yeah, let's do.
Yeah, and then next to it, to the right. That's 3 lines. There you go.
So
So actually there's no...
yes, okay, so it's,
you don't make any assumptions on the restrictions from E to B prime.
you will get assumptions.
Well,
Let me so
a set of assumptions.
okay, so let me slowly go through and talk you through, and you see where the difficulties arrive and what we have to require.
Okay.
So first, in order to build the fiber product, obviously the E to A and the E prime to A is enough to formalize the fiber product. So I have E cross phi prime, E prime in E cross E prime, and I want to have an M polyfold structure on that guy. Yeah, that is what I want to achieve. So in general, since we didn't have a lot of assumptions, I think there's no way that for a general example that would be true. So we need some structure. So the first thing is that we have, because this is a Cartesian product, we have a better model, a more refined model for E as a fiber product of F with A.
Wait, so B prime is the red stuff? I thought it was the green stuff.
B prime. This here. Oh, that should not be, that should be rather red here. I don't know what happened. I mean, assuming this is red here. But don't worry about this, it will come.
You drew B as being green.
Yeah, B is green. This is B prime. So B is the thing closest here.
Okay.
When I glue the things together, then this would be, in fact, the one which comes from the other black box, the B of the other black box. So therefore, ultimately, I will already assume that I have two annuli here for both black boxes, and they should just cross. So the furthest away should be the closest for the other, and the other way around. So that will be the end. So now here's a more appealing model for E, and rather than viewing this thing here, I get a similar construct. I can write this here as F cross phi 0 psi 0a cross, then here this would be phi 0 prime of F prime. Yeah, so these are pieces F, A, and F prime, so that the restriction to the B here is the same. Yes, so that is yeah, okay, so let me, okay, so maybe here I should, so this has a projection onto, so maybe here I should have pi 2, projection onto the A, projection onto the A factor. Okay, so let me just, so would be projection onto the A, and then here phi 0 prime. or maybe here, let me take an even better model here. So this is then here I have f prime cross phi 0 prime cross psi 0 prime A.
Can you write phi 0 and psi 0 on the...
And then here,
Can I
I have,
Helmut, sorry, I think I have a suggestion that will make notation much
yes,
better.
pictures.
Could we, instead of phi 0, just write sort of restriction or R sub, where you denote somehow the domain to which...
Yeah, but the domain, this is already abstract. This is not domain anymore
Yeah,
here.
but still, we need...
No, well,
So phi 0 and psi 0 are all restrictions to B, right? Or let's instead...
no, I think it's easy to understand here.
Instead of the phi 0 psi 0, let's write the
Okay,
domain
I mean, okay. So let me. Actually, this picture is much easier to understand. So,
No, it's not.
huh?
I find your notation easier to understand.
Here's a picture. Thank you. So, right, let me view this as an object where I identify. So this is my f object, and I take just the f presentation. Then I take an element in A and take this, and say they should coincide here. So this is an f, an A, and an f prime. And what I require,
Are we talking about the E's now or about
yes, an element here can be written in a different way because I have this I have this Cartesian diagrams. So let me start. So what you want to have is that the element f is an f, A is an A, and f prime is an f prime. So now you want that the restriction of this to B, which is psi, well, the restriction of f phi 0 of f is a restriction to B, should be the same than the restriction of A to B, which is psi 0 of A. Then you have here this restriction here, which is psi 0 prime of A, is assumed to be phi 0 prime of f prime. That is an element in the fiber product in that description. You have just this short piece here, up to here, and then you have this annuli thing, and then with the other black box and the short piece that should coincide on that annuli.
But F doesn't restrict to A.
F,
F and F prime are an E.
no, so A restricts to B prime, and F prime restricts to B prime. Which is that?
Psi 0 also A. What was A is in B then?
A is in A. Here, A in A. Hmm?
The pi 2 maps are just the induced maps from the E's to the A's. And so you're taking these two, cross products.
So I have this thing.
You're putting them like this, and then taking the third part.
So rather than saying this thing has the same, so I'm looking at pairs of things which have the same restriction to A. But I say alternatively, since an element in E I can write as a fiber product here, which says this restriction is the same than this, then I require that this restriction is the same than that. So I write it as a different fiber product. So what you have to show is now that this thing here, which is a subset, is a sub-polyfold of that. So I have to construct a local retraction. So without any assumption, that's impossible. So here's the fix for this, and the fix only involves this things, B and B prime. which are common to, which belong. So if I consider now a black box having actually this additional features, yeah, it is something which I can say in terms of one black box. I make that precise now. So let me make a definition. So let me call this an enhanced black box is a Cartesian diagram together with an SC map from A to a B prime, so that now I can formalize in terms of these structures which I have here. So this psi 0, let's call this psi 0, 0. So now I have to make a statement about the behavior, the relationship between psi 0 and psi 0, 0.
So the enhancement is just so we can glue our black boxes together.
The enhancement is used to say that if I glue black boxes together, I get fiber products which are actually subpolyfolds. So what you have to require is the following. Okay, so that the following holds. Given A0, 0, so given element in the diagonal, there exists an open neighborhood U of A0, 0
Is it phi 0, 0 or phi?
0, 0. This is 0, 0. I will have better notation in the paper. You and an SC smooth retraction R from U into U such that the following holds. Such that, first of all, R of U is U intersected with the diagonal in A. So you retract to the diagonal. And if HH is R of AB, then phi 0 of H is phi 0 of A. And the other thing is, what happened to my black box here? And phi 0 prime of H is phi 0 prime of B. So what does that mean?
What R is defined when?
I mean, no, I called them psi up. Damned. What did I? Oh my God. Oh, this is psi.
Actually,
Okay, so this is psi. This is psi 0, 0. And this is psi. Okay, sorry.
what is R?
Is a retraction.
On A times A.
U is a neighborhood in the diagonal.
There exists.
Yeah. So now, you see what happens here is you retract on, so if you have a pair AB close to an element in the diagonal, you can retract it into the diagonal so that the restriction of the outcome, if you restrict it to B0, is the same. And if you restrict B to the B prime, it's the same as this of the H. So that means on the left-hand side, the H stays the A, and on the right-hand side it stays a B. Suppose, so here's a diagonal, and you have two different elements. So let me draw them like this. Then you map them into the diagonal by keeping this the same, this is, say, the A, and this is a B, and you keep this the same, so you in some sense connect them like this in two copies. Yeah, so look at this. So you plug in A and B. Now the A, so A and B lie in A. So here's our A. And here I have a restriction to B0. And here to what is it, B prime. So now I take something in the diagonal, a pair close to the diagonal. Then it's being retracted to the diagonal so that this restriction stays the same. It's the same than that of A. And that restriction of the image is the same than the B restriction. Why is that good? It's good because these things don't change the boundary condition if you view being restricting as a boundary condition. So take a point in the firebot product here. So we have F, A, F prime, and it satisfies the coincidence and this overlaps. So now I modify them so that this is not true anymore. So modify this to a G, and well, let's see what I've done. So here's a proof in need of the theorem. So what? Maybe I'm proving something. Oh. Okay, yeah, so do the following. So,
Are we talking about how to construct that R or what to do?
no, what to do with this.
Okay.
So, let me replace this by this. So I take another copy of A here, and this thing here lies in the firebot product of F with A. And this thing here lies in the firebot product of F. So if I flip it, yeah, phi 0, psi 0 prime A. So now, recall that were already M polyfolds here by assumption on the Cartesian product. So now, if I modify data here and data here, so I embed this in this way here and show that that is a retract. So of course then you can ask the question, is that the same smooth structure and so on? And the answer is yes. So I'm not going to prove this. But so I view this kind of things here as lying like this in this product here, which is an M polyfold. So now take a neighborhood of this thing here. So the neighborhood would be some G, U, and a V, Q, let's say. But this thing belongs to this fiber product and this to this fiber product. But it will not lie in the diagonal here. We'll have this two A's. But now I can map this thing here to G, H, H, Q, where H is just this locally guaranteed retraction. And since it has this condition here, it will, well, this A is being changed to an H, but the boundary condition on that side is the same than of A, so it still belongs to the fiber product. And the boundary condition of that H here on that side is the same than that A here, or the same as that B. Yeah, it's the same than that V. So this H, this belongs to that fiber product, and this belongs to this fiber product. So this is a smooth map defined the neighborhood. Is obviously a retraction. Yeah. So the local retraction here can be extended by the identity outside. Yeah, because of this condition here. So therefore, that is a sub-polyfold of this. So therefore, a black box now, say enhanced black box. So this was a definition if you have just one end. So the right picture to view this is that you have something like a, so that's this white here. Then we have the A here. We have the green thing here, which is the B. We have a B prime here. The blue is the A. And that is the infrastructure to meet where you require that for the B and B prime, you have this property with respect to the A, this particular thing. So now, when you have another black box which has the same picture here, you can plug them together. And so what you need, therefore, is that every end you have to have this additional structure.
You're saying your fiber product now is a subpolyfold
Yeah,
of F times A times
of this fiber product cross this fiber product.
Oh, of that. Oh, so I see. So you're saying, hold on. So you're first saying each of these fiber products is a
Yeah, this was the definition of a black box, because that's precisely the Cartesian product here.
I see.
So that is where you use already to have a black box, and then you use this enhanced structure here with the B's. So a black box ultimately is something like this with this. Let's call this a plug here. The plug has this additional structure. So I talked about for spaces. Then rather than polyfolds, you can talk about tame polyfolds things. Then you can have bundles over this, strong bundles over this. You can have sections over this. Then with the sections, for a sectional black box would be a section for all the. So instead of having a diagram of polyfolds, you can have a diagram of strong bundles. Each would have a section, and they should be compatible with the maps which you have over there. So that's the state of the art. What we're currently trying to clean up is to define the notion of a pre-Fredholm problem, if this represents a bundle. And then the result you would like to have is if you can plug two pre-Fredholm problems together it will be pre-Fredholm. And if you end up where there's no free end anymore, in some sense it's closed, the theorem should be this is Fredholm.
So who are the three Fredholm problems that get tried together?
Okay, so when I draw this picture here, at the moment it represents for everybody spaces, other spaces and relationships between them, yeah? I mean the colors and so on. So rather than doing it just for M polyfolds, where all the objects are M polyfolds, I do it for strong bundles. Same type of picture, represented by this. And then I could do it together with given sections, so that the sections are compatible with the maps which you have. So each bundle would have a section. And it would be compatible. So I could talk about a section of a black box. So then what I want to define is, I want to define what a pre-Fredholm section is.
Right? And I thought you said that it's pre-Fredholm if you can glue it with something.
Yes. So that is a possible definition. There are other definitions, possible definitions. So it could be that you have a section here, you call it pre-Fredholm, provided you can find a combination of other black boxes you put together that there's no free end and this thing is Fredholm. And there is presumably a theory like this. And then, but what you want the following result. Whatever your definition of pre-Fredholm is if you can plug two boxes together and you still have free hands, you want to say that that is still pre-Fredholm. And that's the one conclusion you always want to have from that definition. And the other conclusion is, if there are no free ends, it should be Fredholm.
So it's unknown if you take your definition of pre-Fredholm, being able to glue on other stuff to get something Fredholm. It's unknown whether or not if you glue two pre-Fredholms to get something.
Yes, I think it's presumably wrong without, you need a little bit of additional structure. So I know what the additional structure is in the applications, and there we have this, but it's a little bit too special for me. So there might be more general way to say it, but that I don't know yet. And yeah, so then with this formalism, a clean job of a construction would be you construct a nice box, show it has a pre-Fredholm property according basically to this definition which I told you. And then if you know, we have to add, of course, some conditions for the pre-Fredholmness. And then if we're successful in doing this, we will have the results that if you any pre-Fredholm box which are plugged together gives pre-Fredholm and so on. And then you can go back to our say Gromov-Witten problem. So you fix a stable map there. And when you look at what you get, this thing will consist out of a lot of standard pieces like gluing at nodes and some fixed Riemann surface with boundary on which you change the complex structure. So you need some kind of universal thing there. And then for each of these pieces, you construct a black box. So for example, one will look like this. This will be for a finite union of noded disks, which you remove. And I just write one thing here because I view this as associated to the product of the things. You can, of course, since you have automorphism groups action, you want to do the whole constructions equivariantly. And then, so this would and this, and then when I cut this out, then the remaining thing would be Riemann in surfaces with boundaries and maps on them. Of course, I would have a moduli, and I would build another black box out of this. And of course, here, this is the same than this stuff here. They correspond in some way. So I can hook this up with that one and get a Fredholm problem. If I know that this was pre-Fredholm, this is pre-Fredholm. So I get a space, a bundle, and a pre-Fredholm problem. So out of this, I mean, these things are, of course, very natural. Besides what the black box is, I will give it a description what it does inside. There's some kind of an assembly map. You take a parameter, an element in the thing, and you can associate to this a Riemann surface with a map on it and certain things. Yeah? And then putting this together, there's some kind of, so if I put this together, I get an M polyfold. It has a specific point in it which corresponds to this thing. There's a section and so on, and I go into this, I get a map. This is this bundle over the stable maps. So I get some functor here, there, which describes locally the Cauchy-Riemann. And here I have the Cauchy-Riemann section. And then this would be this construction which I told you before, this local parameterization. And then I would have to verify that it satisfies the properties which I wrote down. But that is quite automatic, more or less, if you make a good construction. The technical stuff is really if you have to write down the gluing at the nodes and so on. You never want to do that again. You want to do it once in your life. So the end of result of this black box is a local parameterization. So what you get looks like this. For an element in an M polyfold, you get, if sigma was this, you get S of A of Q. So there's a gluing parameter depending on Q. There's a J of Q. There's an, in general, you can keep the M fixed. That's right, the Q, a DQ, and a U of Q. You get that automatically. So it will look like this. D, so these were the marked points, nodal pairs. And then I have to write D of Q because sometimes some of the nodal pairs go away and then I have a smaller nodal set. So this comes from an M polyfold and it has associated these things. So then I can give a certain descriptions what it actually means that this how this data behave when I look, for example, for restrictions of U to certain parts and so on. And then by the constructions which you used here, like the gluing and so on, this should, if you put it up correctly, have the property that if you pass two quotients, it's a homomorphism onto an open subset of the orbit space and so on. And then you have to verify if you have a morphism between this thing and another parameter value, that the morphism comes from the outside space. So it's basically the automorphism. But these are usually easy things to verify.
So you may have just answered this question, I didn't understand, but we'll see. So suppose we do this setup. Start with two nodal Riemann, two stable maps, but they're the same stable map, right? So two copies of the same thing. And now I want to decompose each one into two black boxes, right? But the decomposition into black boxes depends upon this choice of this collection of annuli, right? So now suppose I take two different choices of these annuli and subannuli and I make them wobble around each other sort of quite a bit. So now I have one local model that's built off of attaching two black boxes together, and I have another local model that arises from building two black boxes together. And now the question is, since everything started with the same stable map, the question is, now you have two local models sort of which clearly have overlap. So why should those transition maps be smooth?
Yes, that question will appear. And
Will it be answered?
yes, you actually at this point, you would have to do a little bit of analysis because you have to, it's unavoidable. You have to look at, I mean, you know how this changes. So, I mean,
I guess the question is, can the analysis be done on the level of black box?
I doubt it.
Is it enough to have compatibility between?
Yeah, well, I doubt it because when you use different annuli, and also you might have make different choices of J, of this. it will not respect your artificial partitions by annuli and so on, necessarily.
Then what's the benefit?
No, because the benefit is that when two things, so the question is, suppose Q equals 0 would correspond to 0. So let's call this family psi of Q. And psi of 0 would be the original thing. So consider now something in the category which does this. And suppose I claim that if Q and Q prime is small enough, the phi has to come. So this would be for the same thing here at the moment. Then I would say that I want to show that the phi comes from a G, from an automorphism. It's not a priori clear. So then, I think still at this point, what you would have shown is, after this construction, is that if Q and Q prime are small enough, then phi has to be close to an original automorphism, and you can conclude something about the transversal constraints, and you can conclude that phi actually is an automorphism. I mean, the thing is, you have, I mean, the black box comes, of course, with a certain manual, what it says, what you actually did inside. And then you have to use some of these properties. So, for example, I mean, if you look at our Gromov-Witten paper, well, but once that is done, then if you have automorphism from one, and so you have the property that every morphism comes from this, and it goes onto an open set. The quotient goes onto an open neighborhood. Then if you have morphisms between two things that they are smoothly depending is not so difficult. Of course, you have to still quote some results. You can write down what the morphism does. It has to respect certain constraints and so on. So then then there are some lists, some little toolkit you have to employ, and it tells that transition maps are smooth. But there's no abstract way to do it. I mean, the point is, however, that whatever you constructed is already parameterized by a polyfold. I don't think there's a construction which is so nice that it respects all these partitions. I mean,
I guess maybe another question then is, so presumably you'll write down all the black boxes for, say, Gromov-Witten. I mean, when you do SFT, for instance, you'll at least have to do the Gromov-Witten stuff. Right?
Yeah.
So this reinterpretation. So then, if one wants to extend the theory further, either Gromov-Witten to boundary or SFT to whatever, right? The question is the new analysis that has to get done to show that the transition maps are smooth when you piece these black boxes together. I mean, do you think it's essentially that you're going to provide a recipe, you're going to have to do this construction yourself, and that when someone else wants to build onto the theory, they essentially just have to follow the same type of construction that you do for to prove this result in the Gromov-Witten case? Or is it actually going to require non-trivial, more hard analysis?
I wouldn't say it is. I mean, the thing. What would the thing here be? Is you would have a family of biholomorphic maps between different Riemann surfaces, and the Riemann surfaces approach those which you originally were of the original object here. You know the things were stable, and you can show that these things in some sense have to converge to an automorphism of the original thing. But while they're doing this, you find out that phi has to map a certain number of points into itself from the constraint construction, and from which you can conclude that the thing is C infinity close to an original automorphism, but belongs also to a somewhat larger finite subgroup. So it has to be an automorphism if you're sufficient close. So there's this analysis what we have in this Gromov-Witten paper at the end, where we show that when we restrict that map a little bit further, that all morphisms come from G. So this is a page or two. I think you can't avoid that. I think there's no way around this. So
But you think that this question of whether or not these new transition maps are smooth essentially boils down to something like this.
yeah, so then if you have two such families here, of course, in the black box description you get a little bit more information how these things depend here. Then if you have a morphism for two different parameterizations between these two things, then the first is that you find that by the construction, I think, that should come out from the construction, that this phi at certain points has to satisfy certain constraints. And then this constraints by construction will move SC, so that it will be sort of SC smooth dependent. So I would say that what will happen for the transition maps are certain terms which occur like in the Gromov-Witten theory. Like you have to look that certain expressions, like you do gluing, then you take a map from a cylinder into itself, but it might not be the identity near the boundary. Compose it with this and then glue backwards. That is smooth. I think that you have to assume that is a known result. I mean, there are definitely certain number of things which you have to verify. But it's some kind of a standard type stuff, which you say there's a library and say whatever shows up belongs to the library and has been proved to be smooth. So it's not so that you don't have to say anything. The theory tells you it's automatically true. I mean, I think that's, well, I don't know. Maybe it would, of course, be great to have such a theory, but not clear to me. Yeah?
How about, so essentially right now we just have these little disks near the nodes, right? And you have the transition maps on those annuli. And if you have two sets of these coverings, shouldn't there be like an enlargement where both annuli lie in a larger annulus?
But there should be an enlargement. I don't know.
Right, you have this covering of your domain, right?
Mm-hmm.
That's what gives you the two black boxes, right? So now, if you have two coverings of your domain, right, two different black box decompositions, right? Then the issue is, how do I know that my transition map is
Mm-hmm.
smooth, right? And I would like to prove this on the level of, I guess, just transition maps between the black boxes.
Yeah, but some part of the which was covered by the black box here might actually correspond to another black box there.
Exactly. So I'm saying you can't hope that the intersection of the two coverings will be nice. But then there should be a third covering so that the intersection, so that, right, the annuli. So you have two sets of annuli, right? And they should each lie
Yeah.
within a larger annulus.
Yes. Yeah. Okay. So.
You take your annulus, you take two copies of the same annulus to start, and then on one you draw this little sort of finger and twist it around and do something strange, and then you do the same thing with this other one. Yeah, you add in a little, I mean, you draw a line, you have an annulus, and then you take it. Yeah, but you take it, now I'm changing the annulus to say this is the annulus I'm going to give you, and the annulus I give you has this little sort of strip that comes up and it rounds and it's top.
Okay. So.
Well, but I mean, you could pick your annuli from the beginning to just be complex disks near the node. Right? There's not so many choices of those.
Here. So let me make a really crucial remark here. That these constructions are so natural that if you restrict them, so you construct this surface here, and now when you glue a surface here, you can always talk about the core region. So let me call a core region something which is a region in the complement of the nodes. When I glue things together, then the glued surface have also a region which I can identify as a core region. So, for example, the constructions are so that if I restrict to a core region, the maps will be SC smooth. if I restrict to anything around the nose, the things will be smooth. So there's a whole list of things which are natural, which is part of the black box description, which will actually allow you that if certain things were chosen a different way, they would be actually still compatible. But it will not be zero. At the end, you still have to say certain things. But there will be a sufficient amount of small talk, meaning you can cite certain number of results, which will take the bulk of the work away. So the basic thing you have to understand is if you have two different families, you get something from the first to the other family of biholomorphic maps. And you have to say something about the properties of this. And you can discuss most of this on the level of black boxes. Yeah.
So I have a question much before black boxes. Namely, so we are primarily interested in studying holomorphic curves. And that's not a regular problem. I'm talking about transversality. So you perturb by these SC plus sections. And you get a compactified moduli space on the nose, which is a smooth manifold with boundary and with core.
If you're lucky.
If you are lucky. Suppose you are. And so my question is, what are the geometric properties of solutions in the zero set of this perturbed section? Like for example, the holomorphic curves have important properties, like if you want to cross some region, space, you need some definite amount of energy, stuff like that. So do these survive with the perturbed things?
Right. So if you do it in a concrete situation, you could actually show that there are enough SC plus sections which have the property that the support would be away from the nodes. They're sufficient to make regularity. I mean, in a particular situation, you can identify subclasses. Then the things which you get are sufficiently close, I mean, even C infinity close to the other guys which are purely holomorphic. So they will inherit properties of them.
So you have this property that the new guys will be C infinity.
Yeah, you can have them as close as you wish. Yeah.
Yeah, then
K goes for every K, for any given K, right? Or can you get the C infinity close?
I think what C infinity close actually means for sufficiently K close. Fresh, yeah. So you can control up to finite derivative.
What do you even mean by CK close if your solution set is a manifold which contains nodal curves?
But
What does that mean?
But the manifold, the manifold containing nodal or non-nodal curve has a smooth structure.
I'm sorry, what?
I mean, it's close on the EK level, on the K level. Well, that is precisely what it means.
What does it mean for a
EK
nodal
is,
curve?
no, well, EK makes sense because that contains.
But that means very much like how it behaves. That the thing will, the nearby thing have very long stretch neck, and the thing will be very close to the curve on the nodal. So you can make that explicit what that means. It actually is really for if you write the nearby things, you can write as a plus gluing. You do plus gluing by things which are CK close to the nodal curve, the maps to the nodal curve. It means precisely what you think it should mean. I mean, any not noded curve near a noded curve can be written via a gluing construction. And what I have to glue are things which are as close as you wish to the noded curve, to the data of the noded curve. So, I mean, it's precisely what you would think it should be. No, he asked. So we have a discussion. What does it mean? A non-noded curve is C infinity close or CK close to a noded curve. And what one means by this is, if I find a spot here, you would, so suppose the noded curve would be U. Let's say go from this into Q. So then I would have a gluing parameter here to glue the things together. And I would write x of U psi, glue, and glue the things together here. And I would say this is CK close, provided A is sufficiently small, and the psi is CK small as well. This thing would be a curve which is non-noded. So what this means is I take a vector field along U, take the exponential map, and then I glue this by taking the component which I have here of this object here and the component here, and cut this off with a cutoff function and add plus 1 minus beta, another cutoff function. This gluing construction which I showed today.
So I have another question. Again, assume you take the perturbation of your problem. You get your compactified solutions at 0. Now, there's also the initial compactified modular space for your problem without having perturbed.
Mm-hmm.
Does the perturbed one converge, say, in Hausdorff distance to the non-perturbed one? You have compact.
I mean, you can take a CK neighborhood, well, you can put all kinds of metrics there.
No. Not in Hausdorff, right? Because it could be the case that you perturb and then something vanishes. You have a non-generic curve which should not exist. So
Yeah, it could be that, but in Hausdorff distance not, but only in the sense that you can take an epsilon neighborhood around the unperturbed stuff and you will lie in the epsilon neighborhood. And the epsilon neighborhood can be on any level.
No, but if you have
Of course.
totally ungeneric nodal solution someplace,
they're isolated.
isolated,
that
would perturb, you would just make
Yes.
it
Just a point which goes away.
The empty element lies in any ball, I think. So what I'm just saying,
You're not getting a new solution, I see. So you're saying
what I'm saying is if I take the unperturbed problem and take an epsilon neighborhood around the whole set on any topology I want, CK and up, then I can take the perturbation so that it lies there.
but not Hausdorff distance.
Yeah, Hausdorff, of course, the symmetry doesn't work because. Yeah, so I mean, you can definitely play around. So, for example, what is nice to keep is sometimes the behavior near the noded region. You don't want to have perturbed there. You want to have it holomorphic there. So then you can take SC plus sections in this concrete case, which are supported away from the nodal areas, and that is sufficient to make it transversal. Then, of course, you can, of course, play around with the J as well. So that would be giving a different Fredholm problem and make things as generic as possible already with the J, and then make.
That's weird. If you perturb the J, it's not an SC plus.
No, it's not SC plus, but it's still a Fredholm perturbation. It's a family of Fredholm operators. So you could make the things as generic as possible, and then on every component which is already fine, you don't need any additional work, leave it. And there, where you need additional work, you take a small SC plus section. So you can keep what you can achieve in the classical situation, and then the other situations you have to resolve with SC plus sections.